All right. Good afternoon, everyone. We will start here. So the last time we met, what was the last thing we did? We discussed up to which part? So we were in HBR addition. Right. So shall we take down a small question under that? Right. So the last thing we did was the mechanism of HBR addition, right? Yes. Okay. Let's take a small question down. We'll see whether you remember the theory parts we have done in the previous week. Write down a small question. For the following molecule, draw the mechanism of addition of HBr. For the following molecule, draw the mechanism of addition of HBr. And explain what would be the major product and why. And explain what would be the major product and why. Now, I want you to show both the types of products that are formed, and I want you to branch out the mechanism to show the production of both of them. Can you do that, please? Can someone name the major product for me? Any names that you would like to say? Which one out of the two is a major product? Top one? You also say top one? Why is top one the major product? If you're saying top one is a major product. Again, so you have to say, what's more stable? So this is a mistake that students says. What is the most stable one? This one. So now you guys use the word more stable. What is more stable in this? The carbocation. Don't say this is stable, okay? This is not the one that is stable. This is the one, in the sense, when you're talking about stability, we are comparing the stabilities of carbocations, right? Not the final product, okay? So always compare the stabilities of only the carbocations and say the tertiary carbocation that is formed here is more stable. Because of that, the tertiary carbocation is formed more than the primary, in this case not primary actually, secondary carbocation. This is secondary carbocation, this is a tertiary carbocation. Always comment on the carbocation stabilities, not necessarily the final product's stability. That is something that you can't necessarily comment on. Is that understood? Yes? So, we have to say what do you call it? Out of the two products, the very first product, which is going to be named 1, 2, 3, 4, there was 4 carbons, so we can say 2 bromo, 2 ethyl butane. 2 bromo, 2 ethyl butane product is the major product. We have, then after that we have this other product. Oh no, sorry, not 2 bromo, 2 methyl. My goodness, no, that's not the major one. We have 1, 2, 3, 4, 5. 5 carbons are there in the main carbon chain. Don't make the mistake that I did. So if you name it from either direction, on the third carbon we have bromo and a methyl group. So we can say 3 bromo, 3 methyl. With this one is 3 bromo, you should name them. 3 bromo, 3 methyl, 3 methyl butane. Now this one is going to be 2 bromo, 2 bromo, 3 methyl. This is not butane, sorry. I'm sorry, this is not butane. 1, 2, 3, 4, 5, pentane. So this is also 1, 2, 3, 4, 5, pentane. So you need to make sure that you choose the longest carbon chain. So you can say in your answers, this is a secondary carbocation. This is a tertiary carbocation. So you have to say the tertiary carbocation is more stable. Therefore, this product, you can write the name of the product, is produced more. Is that clear? You have to always talk about the carbocation before talking about the final product. Always keep in mind. I don't know why it doesn't go into many students' heads. Like I keep saying this. Now you are not the only class. No, most of the time, after about a week or two, when I ask this question, they will come up with something different than what I said. Can you please remember this? Since I am telling you this now, don't mix it up. The carbocation is the major component here which decides what gets produced more. Obviously the stability of these two carbocations are different. This one is less stable, this one is more stable. When the mechanism takes place, the more stable variety gets formed, obviously, right? And then through the more stable carbocation, this gets produced. So since there are more, this one has gotten produced more, the final product, this particular final product will be there more. Is it understood? Right. So that is what has happened here. Keep that in mind. Now, did we speak about Markovnikov's law and anti-Markovnikov's law? Write down a new heading, Markovnikov's law. Markovnikov's law. Oh, sorry, so you would know the name, right? It's like this, Markovnikov's law. So many V's, definitely Rashid, right? I think. So Markovnikov's law. Write down. Markovnikov's law states that when adding a monoprotic halide, within brackets write HX, across a double bond of an alkene, the hydrogen atom will get attached to the carbon atom with a greater number of hydrogen in it. Carbon atom with greater number of hydrogen in it. So let's break it down. So in this case also it is visible. Now for example, this is a monoprotic halide, let's say HBr, HX, right? Usually X is used to define the halogens. So if you have this hydrogen and you want to attach it to either one of these carbons, you have to ask yourself, out of the two carbons, which one has more hydrogen in it? Now this carbon doesn't have any hydrogen. This carbon has one hydrogen attached to it. Is that clear? So where would this hydrogen go? To the carbon where there is more hydrogens. Now for example, you go to a party. Two groups are there. One group, all unfamiliar faces. This group, you have a familiar face. What do? You most probably will end up going there, unless you don't like the familiar face. So usually we go to where we are familiar with, right? So just like that, right? So Markovnikovs have suggested, based on the actual mechanism that is happening, he is suggesting that H or hydrogen will get connected to the place where there is more hydrogen. So for MCQs and all that, this law is super useful. Why? When it comes to MCQs, they ask what is the major product when something like this is happening. At the exam, are you going to write the mechanisms for a MCQ? No, right? You don't need MCQ, to draw the mechanism for an MCQ. You can use Markovnikov's law. Hydrogen is great, there's a great number of hydrogens here, so therefore you have the hydrogen attached to this carbon and Br will get attached to this carbon to form the major product. Is that clear? Is it understood now? Right. Then write a new subtopic. Do you need an example for that, like the previous one? Write down in the above, in the previous one, for this, you can write example. In the above example, or in the above question, three bromo 3-methylpentane was produced following Markovnikov's rule. So this is the major product. This is our major product. So major product always follows the Markovnikov's rule. The minor product is usually something that gets produced quite less, like maybe about 5-10% of the time. 5 to 10% of the time. The other one is a major product. Okay? Right. Then please write a new topic. Anti dash Markovnikov's addition. Anti Markovnikov's addition. Write down. When adding a monoprotic halide, across a carbon-carbon double bond, you can write CC double bond like this, across a carbon-carbon double bond, we can attach the hydrogen to the carbon atom with less hydrogen, by adding a peroxide into the reaction mixture. This results in producing a product. That follows the opposite trend seen in Markovnikov's addition. We'll write an example down. Example. We'll take a simple example. CH3 we'll take a simple example like so. If I added HBr here, students, if I just normally follow the Markovnikov's addition, tell me where the hydrogen should be attached. This hydrogen should be attached to which carbon? This carbon, right? Do we all agree? And the bromine will go here. Yes? But if you do anti-Markovnikov's addition, what happens is hydrogen will not go to the place where there's more hydrogen. It will go to the place where there's less hydrogen. So we achieve that by adding a peroxide. Now students, we indicate the peroxide like this. We can take an organic peroxide, or we can just add hydrogen peroxide as well. That is not a problem. We usually add organic peroxide like so. And then you produce this CH3C we have these hydrogens from the previous part. So now I have to add the hydrogen to the place where there's less hydrogen. So HBr hydrogen can go either here or here. So now this carbon has less hydrogen, so I'm going to add it here, and then Br here. Is it understood? Right. So this is a peroxide. Now just to remind you what a peroxide looks like, I don't know whether you remember the formula for peroxide ion, O2 2 minus. When you're talking about oxidation numbers, we would have discussed this. So a peroxide ion looks like this. Now here what we are dealing with is a organic peroxide. So there is a alkyl group attached to these oxygens, right? So we would have 2 lone pairs on each case. Is that clear? That is also referred to as a peroxide. Understood? You are familiar with hydrogen peroxide. We discussed this not only when it comes to oxidation numbers, but also when it comes to unit 6, right? We discussed peroxides, but not organic peroxide. We discussed hydrogen peroxide. The whole book shape of the molecule, can you remember? So is that clear now? Understood? Great. So after this we'll move on to the next part. So take this down as an example. So today, students, we are going to go through many chemical reactions, organic reactions, and many mechanisms, and we are going to finish off as many reactions as possible, and then we are going to move on to conversions. I can't do conversions without you having the conversion knowledge. So you need to first of all know a few reactions for me to give you a conversion, right? So today we are going to be doing that. So keep that in mind. Right, shall we quickly move on to the next part, right? Is this clear to you, right? So this equation is something that flies under the radar, meaning now when we do conversions, now today we are just starting like little bit of conversions, but later on we are getting into conversions a lot. So majority of the time, although this memory is quite fresh right now to you, after a while you forget this, and then for certain chemical reactions, you will realize without this, you can't do the conversion. So this is some reaction that for many students, that seems to be not very important, but keep in mind, this is like one of the most important reactions. You will see it becomes like a missing piece in certain conversions. Now you can put everything together, and if you don't remember this, you can't connect the two ends together. You will not be able to complete the conversion without this. We don't use it all the time, so students forget about it, but later on they realize the importance of it, right? So this is a unique important reaction. Keep this in mind. Understood? Right. So after that, now we move on to bromine addition. Now students, bromine addition is super simple. It's just like HBr addition, but I need to explain a little bit about this bromine addition. Now if you are bear with me just a second. When it comes to addition of bromine, we'll take a simple molecule here. If you feel like we are moving fast today, students, keep in mind we are not. These are basic chemical reactions you should be familiar with, and mechanisms we'll take it slow. I will make sure that mechanism part is clear to you, but other than that, the equation part, it's not that difficult, something that you just have to remember. Okay, so now if you take HBr addition, we saw when there's a delta positive group, this double bond double bond and delta positive group will interact and form a bond. Now can someone tell me, why do alkenes usually react with electrophiles? What is the reason? I have explained this to you. I want you to tell me, why do alkenes react with electrophiles? What could be the reason? Alkenes are? No, all the molecules are relatively okay, stable. There's no. Why do they react with electrophiles, not nucleophiles? They normally react with electrophiles. Sorry? Free electrons. Alkenes, do they have free electrons? Sorry? Less than electrons. Alkenes. No. So if they have, for example, if they have excess electrons, it will be negative. If they have less electrons, it will be positive. Right? So now I discussed this. So what is the reason? Anyone? So alkenes have what? A double bond. Now double bond has what? A sigma bond and a pi bond. Now when it comes to a sigma bond, students, right, I will draw this for you now because you are finding it a bit difficult to remember this. Or if I just mention there is a high electron density on a double bond, I just need to give it to you now so that you can picture it better. So these are the carbon-carbon nuclei. This is carbon nucleus, this is carbon nucleus. This is the region where the sigma bond electrons are. This is the region where the pi bond electrons are. Right? So sigma bond electrons are very tightly attracted to the nuclei because they are in between the nuclei. We say along the internuclear axis. So these guys are very strongly attracted. What about these guys? They are not very strongly attracted and they are above and below the sigma bond, right? And they are more exposed to the outside. So these are electrons that are exposed to the outside. So what happens, it's like, for example, there are certain parts in the country, like if you are going out and all that, people say don't wear all of your jewelry and go, right, don't show it to people a lot. What happens? There can be people who will come up to you and ask you for the jewelry, like, give me your jewelry. You have to end up giving them then. So just like that. So electrophiles are electron definition groups, right? Electrophiles. So when they are present very close to these exposed electrons, they can interact. They can pull electrons and have a bond with them. Is that understood? So that is why usually double bonds react with electrophiles. Electrophiles are electron deficient groups and they can interact with these electron exposed regions of the double bond. Is that understood? Right? So here also, now if you take bromine, students, and now this example, the reason why I brought it up is this. If you take bromine molecule, when you are adding bromine to a double bond, the bromine molecule is symmetric, and since it's having the same electronegativity, these two atoms, there is no polarization of the bond. So what is this molecule? A non-polar molecule. Do you agree? Right. So the non-polar molecule is slowly making its way closer to this alkene. Now as it reaches the double bond area, what do you think will happen to this bromine molecule? Now there are electrons here. This double bond has a high electron density around this region, right? So this is also coming towards that part. I imagine these kind of electron density regions are present here. So this is also coming close to that part. Electrons and electrons. The bromine's outer area also is filled with electrons. Around here also there are electrons. Electrons and electrons, do they repel or do they attract? They will repel, right? So as this molecule slowly comes close to this, bromine's electron cloud will be repelled by the outermost, the electron density of the carbon-carbon double bond here. Is that understood? So this creates a polarization of the bond. Understood? So since the electrons are pushed away from the front bromine, the bromine atom that is in the front here, around that area electron density will drop, and this bromine will be partially positive, and this bromine will be partially negative. Is it understood? So this happens as the bromine molecule approaches. Now I don't want to have that part, that is for your understanding only I drew that. So that happens as the bromine approaches the carbon-carbon double bond. Is that clear? Understood now? So from here onwards, this section is now electron deficient, so we can call this an electrophile, because it is electron deficient now, because its electrons are pushed more towards the other bromine. Now this guy has a low electron density, so it is an electrophile. Now there can be a bond formed between carbon and bromine. Is that understood? Now it's somewhat similar to HBr addition, but not entirely the same. Similar to HBr addition. Is that clear now? Understood? So when this bond is being formed, what will happen to this bromine-bromine bond? It will break, and those electrons will be given to the other bromine, because you can't have just electrons, this entire thing connected to one another in a linear fashion like that. So this bond will break, and the bond electron will be given to the second bromine atom here. Now what do you think will form? I told you this is similar to HBr, not exactly the same though, because they form something unique. The initial starting point is somewhat like HBr addition, but this particular mechanism is somewhat unique to most other mechanisms you see. They form what is known as a bromonium ion. Nowhere in any other mechanisms you will see anything like this. Is that clear? They form what is known as a bromonium ion. So this bromonium ion again is not that stable. So what happens is a bromine, now you can say this bromine atom has turned into a bromide ion now. Why? Because when this bond broke, the bond electrons were given to this bromine. Here are the bond electrons. Now it is negatively charged. Now what happens? This can attack this carbon, and these bonds will break, finally forming this. This is called the addition of bromine, Br2, to an alkene. Is that clear? Very simple reaction when it comes to reaction wise. Br2 turns into this. Sorry, alkene plus Br2 produces this. But the mechanism wise, you need to remember each step. This is a bit of a unique mechanism. All the other mechanisms you can just predict and write. I will show it to you. Once you learn one mechanism, you can do all the other mechanisms without any issue. I will break down how the mechanisms work as we discuss more and more mechanisms. But this one is a bit unique because of the formation of what is known as a bromonium ion. Is it understood now? Right. Shall we take this down under the addition of bromine or bromine addition? Take it down, students. Now after a while, students, you may forget why Br was partially negatively charged. Okay, so I will show that, like, you know, I will explain that to you in this diagram. You can take that down as well, because some students forget that after a while why bromine was written with a negative charge. Sorry, not negative, partial charges. So write down a small explanation to that. Please write. Br2 is a non-polar molecule. Br2 is a non-polar molecule. Br2 is a non-polar molecule. As the Br2 molecule approaches the double bond, the pi bonding electrons of the alkene will repel the Br2 electrons and cause a polarization of the Br2 molecule. Can you please take that diagram down? So the arrows indicate that they are moving towards the double bond, and as it moves towards the double bond, that's what happens. Creates a polarization of the bromine molecule. Right. So the arrows indicate they're like they are moving, it's in motion. For alkenes, all the reactions, these pi bonding electrons are the reason. They are more exposed, and electrophiles will interact with those exposed electrons. Right? So pi bonding electrons are the reason. Got it now? Right. Under that, please write. After that, please write as a new star point, right? This reaction readily takes place. And is used as a identification for unsaturation. unsaturation. Right. So now students, I will give you one more sentence here. So when you are adding bromine here, you need to know the reagents that can be used. For this, now I need to mention the main overall equation also. I will give that to you. We usually add bromine water in usual lab setup. Bromine water is bromine dissolved in water. Br2 liquid dissolved in water. Bromine water is not as strong in color as liquid bromine, and liquid bromine is reddish brown in color. But bromine water, so bromine water is somewhat yellow in color, orangish to yellowish in color. Normally it's yellow, right? So if you take a little amount of bromine water into a boiling tube or a test tube and add a considerable amount of our alkene into it, like liquid form of an alkene. Most alkenes are in gaseous form, not most, like the very first few alkenes of the homologous series of alkenes are gases. But if you find the liquid form of an alkene, if you add a few drops of it, what happens is the bromine water that is yellow in color will completely be colorless. Right? Why? Because bromine water's yellow color comes from Br2 molecules. If you add an alkene, what happens? Br2 will react with the alkene and then will form this product. No more bromine molecules are there in the medium. So bromine water will be decolorized. Is that understood? So you can write, and the other thing is, if you want to do a similar reaction here, now one thing is you can add bromine water, Br2 aqueous, or you can use bromine in carbon tetrachloride, CCl4. Br2 in CCl4, so then everything is in organic medium, that's it. Right? Br2 in CCl4 also can be used to obtain the same product. Right? Observations are the color of bromine will anyway disappear. Is it understood now? Write down a small sentence here. When Br2 is added to an alkene, or bromine water, Br2 water, when bromine water is added to an alkene, O and alkyne, any double or triple bond will show this reaction. Alkenes have double bonds, alkynes have a triple bond. Any of those will show this reaction. When bromine is added to an alkene or an alkyne, the color of bromine water will disappear. Within brackets just write yellow to colorless. Yellow to colorless. Close brackets. Indicating bromine addition reaction has taken place. Indicating bromine addition reaction has taken place. Right. Then we move on to addition of H2SO4. Write a new heading. Addition of sulfuric acid. Addition of sulfuric acid. Write a small sentence. When alkenes are reacted with cold concentrated sulfuric acid, When alkenes are reacted with coal, concentrated sulfuric acid. Alkyl hydrogen sulfates can be formed. Alkyl hydrogen sulfates can be formed. And then write, if diluted with water and warmed, if diluted with water and warmed, if diluted with water and warmed, it will form an alcohol. Take this down, please. Done? Now can you picture the mechanism for this, students? Right? This is our sulfuric acid. You can take it down for the time being. I will show you the sulfuric acid Lewis structure. This is not something complicated. Right? This sulfuric acid Lewis structure. Can you picture how the sulfuric acid molecule might be heading across this carbon-carbon double bond? Can you figure it out if I ever ask you to draw it? The answer should be yes. Now you might think this looks very complicated. Now anyway, you are required to know the mechanism for this step. The next step mechanism is not necessarily needed. It is not given in the textbooks as well. Now if you take a look at the mechanism here, what we have here is a alkene here, and then we have our sulfuric acid molecule. Now I will draw the sulfuric acid molecule here. Now sulfuric acid, this OH part obviously is quite polarized because hydrogen is less electronegative and this oxygen is quite electronegative, right? All the other bonds are also polarized, but since we know that hydrogen sulfate part is getting added across along with hydrogen, I only decided to show this polarization because you can see this section is added here, hydrogen is added here. Now just picture this as and HBr. What happened in HBr? Hydrogen got added to the place where there's more hydrogen. Bromine got added to the place there was less hydrogen. Is that clear? Same story, same mechanism as HBr. Is that clear? Same mechanism. Now imagine this section to be a bromine section, this section to be a hydrogen, right? So what happens is, initially, since this area is partially positive, the carbon-carbon double bond will break its bonds and give its electrons to this hydrogen. And as it happens, this hydrogen-oxygen bond will break and its electrons will be given to this oxygen. Okay? So it produces these two products. Our first one is this. We have CHH. I'll draw this part in red so that you know what's happened here. So this one is the hydrogen that got attached here, the new hydrogen. So therefore this carbon will be what? Partially positive, because this bond broke, bond electrons were given to this. So this carbon becomes positive, not partially positive, positive. And then this section is still there, like so. And it can start an attack on the positively charged carbon. This one is electron rich because it's negatively charged, and that can attack this carbon. Finally forming what? Finally forming our product. Hydrogen here, OS. So we call this a alkyl hydrogen sulfate. Do you see? The mechanisms don't change, students. You learned one mechanism, it feels like you have learned all the mechanisms, right? Except for the bromine addition one. Bromine addition one is slightly different. Is that clear? So we have this mechanism. So this mechanism is questioned. You should know this. This mechanism is not, so it's okay. That means how the water is added across this. When you are heating this solution with water, we get to this. Is that clear? So take this down, and apart from that, students, you should know the overall reaction. Now how to write the overall reaction? So we usually write it in two ways. We just write like this: CH2, C double bond CH2. We can say first reacted with concentrated H2SO4, right, cold concentration H2SO4, then reacted with water H plus and H2O and heated, and you are getting to this CH3 CH2 OH, right? That's the product that we have finally formed. So basically, if you do these things, eventually what you get is this. We never usually stop at this product, students. In a sense, this is pretty useless to us. We don't use it. What is this for? Like, are we going to do anything with it? Most of the time, no. So this is, after we form this product, we convert it into alcohol, because alcohol has more uses than that product. Is that clear? So that's why we will dilute by addition of water. So addition of water will dilute this medium, and then we heat it. So this molecule, product that is not very useful to us, gets converted into alcohol, which has more uses. So we write it like this, but also we can show this in a much bit of a simpler way. CH2, we just write dil H2SO4 and heat. That also forms this. Actually, the reaction that happens is still the same in both cases. We can indicate it in two different ways. Is that clear? Take this down along with those two. Here the numbering is important if you are writing this method. Okay, this numbering indicates first step, second step. Do it. Question? Was it cold these days or a bit warm these days, like Kampa? Cold in the morning. Today is a bit of a warm day, right? Only when I come to Kampa it happens. Okay, then write a new subheading: reactions with KMnO4. Reactions with KMnO4. Reactions with alkaline KMnO4. Alkaline KMnO4. Okay, students. So now, when it comes to alkaline medium KMnO4 addition, what happens is, now for this one you don't learn the mechanism because we just give you overview of the final product that is formed, not just the actual mechanism, because the actual mechanism is a bit of a complex multiple step reaction. So we will learn only about the fact that if you take any alkene, and if you add alkaline medium KMnO4, potassium permanganate. We can write it like this, OH minus KMnO4. This is called alkaline medium potassium permanganate. What happens is, you will form what is known as a diol, also referred to as a glycol, will be formed. Diol or a glycol will be formed. Right, so this is called diol, also known as a glycol. The name of this will be, actual name of this will be ethane diol. Now in this case, you don't have to write where, in which carbons the OH groups are there, you don't have to write. But if it's a larger molecule, let's say something like a butane or pentane molecule with these two, then you have to say where the OH groups are. For example, you would say something like pentane 2,3 diol or pentane 1,2 diol. Is it understood? Right, here no point writing ethane 1,2 because no, actually I'm sorry, in this case also we need to say that because OH groups both can be present on one carbon, right, when I say diol. So this also we have to say 1,2 diol is important. Okay, first and the second carbon is where the two OH groups are, because there is another possibility. I was going to say there is no other possibility. You can have another possibility where both of the OH groups are present on the same carbon, although it is not a very stable configuration. That is possibility. So therefore you have to write ethane 1,2 diol. We can bring these numbers in front. So you can write 1,2 ethane diol is also fine. Is that clear? Right. So take this down under that heading. And also remember, in OH medium, in alkaline medium, when this reaction takes place, MnO4 minus, that is the reactive species here, MnO4 minus that is present here, MnO4 minus, KMnO4 is added to get the MnO4 minus. Potassium does nothing here. Permanganate ion is the one that is doing everything. It turns into MnO2, which is a brown color precipitate. So when this reaction is taking place, you can see apart from the formation of the organic product, it will also form a brown color precipitate. Now, first of all, take this down. I have to give you a small description here. This is a redox reaction, so I have to give you a small description here. Yeah. Do you all have one card for all the classes here, or each subject has a card? One card for everything. Are you done? Anyone done taking this down? Right, both the reactions. Now students, chemistry is something like, practical. The thing is, amidst all this A-level competition, your stress, you forget this, right? You forget this is a science. Like, there is a base to all the things we do. Now, for example, this particular experiment is done to identify the presence of a double bond or a triple bond. Right? So this is an identification test. And earlier, even bromine addition to a double bond or a triple bond was also an identification test for unsaturation. But reaction of sulfuric acid with the alkane was not an identification test. Why? What is separating these two reactions, bromine addition to a double bond and alkaline medium KMnO4 addition to a double bond? What is separating those two reactions from sulfuric reaction? Yes, you have a very visible observation. Bromine addition is giving you a color change from yellowish to colorless. Here we observe another very visible observation, that is KMnO4 is a purple color solution. Its color will be decolorized while forming a brown color precipitate. Is that understood? So if the reaction is actually taking place, it will give you a very visible observation. And that is why these kind of tests are used for identification. Is that clear? Is that understood? Right. Write down a small, about 3 bullet points, star points. Write down 3 star points. We'll write down the first one. This is a redox reaction. This is a redox reaction. To the same point you can write, while the alkene gets oxidized to a diol, MnO4 minus is reduced to MnO2. That's the first step, first point, right? Second point. This reaction is known as the Bayer's, B-A-Y-E-R, the Bayer's, B-A-Y-E-R, Bayer's test for unsaturation. Bayer's test for unsaturation. As this reaction will take place while producing a color change from purple to colorless, or color change from purple to colorless, while producing a brown precipitate. Okay, so students, whenever they say unsaturation can be tested, unsaturation means any double bond, any triple bond. Unsaturation means double bonds or triple bonds of carbon, right? So this will react for alkenes, work for alkenes as well as alkynes. Is it understood? Alkenes or alkynes will react with this. Both will react with this. That's why we use the word unsaturation. Unsaturation is when the presence of When you have a presence of double or triple bond, it's referred to as an unsaturation. Okay, are we clear? Right. So that's it for diols. Also remember they are called glycols. Now we move on to the next part. Now we move on to the next reaction. Take a new heading. Take a new heading. Hydrogenation. Hydrogenation. Oh wait, do you want a diagram to explain this? Now based on what the observation is, some students forget this. If you want, you can take this down. So if you do this test, this is what happens. You have a purple color solution. Purple color. So as the reaction takes place, the purple color will be colorless, clear solution while producing a precipitate. I need to tell you something though. This manganese dioxide precipitate that is getting formed, usually whenever you form it, it doesn't look like a precipitate initially. Now imagine you have potassium permanganate and it gets reduced to manganese dioxide. Manganese dioxide gets produced as such fine particles, it gets spread throughout the aqueous medium. The medium starts to appear brown. You shake it, it looks brown. And it looks like a brown color solution. Right? So you think purple has turned into a brown solution, but no, that's a precipitate suspended in the aqueous medium. So if you allow it to sit for a very long time, you can see all the brown particles collect at the bottom. Although we draw this observation won't come immediately. The whole brown precipitate coming at the bottom won't happen immediately. What you initially observe is a purple color turning into a brown color. Is that understood? Then only the precipitation takes place. In the sense, the collection of the precipitate at the bottom takes place. The precipitate that is produced is suspended in the aqueous medium initially. Appears brown. The entire medium appears brown. Is that clear? But most of the questions don't trick you like that. They directly say brown color precipitate was formed while the MnO4 minus color is decolorized. So they don't check your practical knowledge to that extent. So it's somewhat okay then. But if they ever ask you brown solution, purple solution turned brown, later on a different observation was obtained. So if the purple solution turns brown, that means KMnO4 was produced. Sorry, KMnO4 has undergone reduction forming MnO2. Okay, right. Hydrogenation. Hydrogenation is something simple. I don't want to explain that. If you take if you take any carbon-carbon double bond or a triple bond, it could work with any double bond or triple bond. Students, I don't have anything to explain here. This is such a simple reaction. If you react H2 with nickel, but you can use nickel, platinum or palladium, Pd. Right? Either one of those metals are fine, but we usually use nickel because it's cheaper. Right? You will produce an alkane. There's nothing to explain. The reason why we write nickel, these are other possible catalysts we can use. Nickel is a catalyst here. Nickel, platinum or palladium catalyst can be used. Such a simple reaction. You actually consume products of this reaction. Anyone knows the product that you consume of this reaction? Basically you eat it. Chemicals, no, you guys eat. What? Margarine, exactly. Margarine. Right? Why do you say it's margarine? Olivers. Yes, exactly. So here, if you take vegetable oils, they are liquids at room temperature. No? That is because, students, vegetable oils have a lot of unsaturation. Now, saturated fats or saturated fatty acids, they look like this. Fatty acids mean they have a very long carbon chain like this. Unsaturated fats, they have a double bond or triple bond in the middle. So having a double bond or triple bond in the middle sometimes cause them to have weird shapes. Right? So because of that, what happens is these kind of fatty acids can't, now triglycerides are there in oil, but apart from triglycerides you can have a lot of free fatty acids like this. Now we'll talk about free fatty acids here. Now these free fatty acids, if it's like this, saturated, you can see the shape of the molecule allows them to pack really well. And these kind of molecules that have a bit of an odd shape due to having unsaturation in the molecule, they can't pack really well because they are irregular in shape. They can't pack really well. So when they can't pack really well, they stay as a liquid. Is that clear? At room temperature. So that's why we have plant oils. Most of the plant oils have a huge content of unsaturated fatty acids. So that's why they don't pack really well and stay as liquid. If I carry out hydrogenation process, which is by doing this, these double bonds will be hydrogenated and will turn into something like this. Now these molecules can pack really well and have stronger London forces between them. So when they pack really well and have very strong London forces between them, it causes them to solidify. So vegetable oils turn into solid fats. Is that clear? So you use the spreadable fats or something like margarine, extra margarine or whatever, is basically produced this way. So we use this reaction. Practical applications are there. Is that clear? Right. No need to take this down. Take this down, and we are done with that part. Right, are we done? Okay. Then we move on to the next part. Write down a new heading. Reactions of alkynes. Reactions of alkynes. Take the first subheading, addition of HBr and Br2. Addition of HBr and Br2. Take this down. I don't want to explain this too much. We'll try to summarize the knowledge we have on alkynes and alkenes later on. So that could be an activity that you also do on your own at home, because we need to be able to have all the equations in one page. So when you're studying, it will be easier. So now what is happening here? Something simple. Now HBr reaction doesn't necessarily require very harsh conditions or heating to really high temperatures. HBr addition for bromines also was easily done, right? Here also the same happens. When you have a double bond, hydrogen goes to the place where there's more hydrogen. In this case, both carbon has the same number of hydrogens. So what happens? Initial step, hydrogen can get added to any carbon here. Initial step. Now after the initial step is done, when the next hydrogen is added, now we have a carbon with 2 hydrogens. Right? You can't now play around. You have to add the hydrogen to this carbon. Is that clear? So anyway, this happens in 2 steps. But this does happen. We can't easily stop here. It goes all the way here. Is it understood? When you have added HBr to carbon-carbon triple bond, this happens. When you add Br2 to a carbon-carbon triple bond, all the way up to this particular product, we will be going and we will be forming it there. Is it understood now? Right. So these are the main things that we produce. That's it. And we can use Br2 addition, bromine water addition to what do you call it, as an identification test, right? Because bromine water will be decolorized even with a carbon-carbon triple bond. Okay? Right. Then write a new heading: hydrogenation of alkynes. Hydrogenation of alkynes. Under that, please take this down. I'll give you a small explanation in a second. There are 2 types of hydrogenations that we see. Basically adding nickel or PT or palladium along with H2. H2 gas is the reactant. Without hydrogen we can't do anything here. So then what happens is you produce something like this, an alkane. Take this down, leave that bottom space. Okay, so now imagine you didn't want to have an alkane. Imagine you actually were planning to take an alkyne and convert it into an alkene, right? Let's say this is what you wanted, not an alkane. Imagine you wanted this to turn into an alkene and stop there. Then what can you do? Then you can't use nickel, platinum or palladium. Now nickel, platinum or palladium are strong catalysts. They are capable of converting this completely into the hydrogen, completely into alkanes. Now these are reducing, we can consider them to be good reducing agents that promote reduction. So these guys are going to be reduced. Reduction is something that is specified as gaining of electrons, gaining of hydrogen or loss of oxygen. Here we can say in this particular process each carbon has gained 2 hydrogens. So this is a reduction. Reduction is specified as, in 3 definitions are there. The most commonly used one is reduction is gaining of electrons. That's the one that we always use, gaining of electrons. But we can't see the electron being gained here, no? There is electron gain here, but we can't see it. So we can also specify it as gain of hydrogen. Reduction is gain of electrons, gain of hydrogen, or loss of oxygen, right? Oxidation is the opposite. Loss of electrons, loss of hydrogen, or gain of oxygen. So now here we can very clearly see this one is gaining hydrogen, so it's a reduction. Now if you use nickel, it will be producing a much greater reduction all the way up to the alkane. We don't want to have that here, we want to stop at the alkene. So we use a specialized catalyst, that is palladium coated onto barium sulfate, right? Barium sulfate. This is a bit of a milder catalyst. To make it even more of a milder reducing agent, we are going to poison this catalyst with a substance known as quinoline. Have you ever heard of the word poisoning a catalyst? Now even this nickel palladium platinum catalyst can be poisoned, right? For example, whenever a catalyst comes into contact with certain substances like sulfur or certain substances with like lead, right, it hinders the catalyst's ability to work as a catalyst. Now catalyst, what is the characteristic of a catalyst? What does catalyst do? They speed up the reaction. Now a good example is in vehicles we have something called catalytic converters. I discussed this I think some time ago. They say in vehicles it's always advised to pump lead free fuel, right? We don't want lead. One of the reasons is this catalytic converter gets poisoned by lead. Is that clear? When lead is there, now your catalytic converter has precious metals in it, platinum, palladium and rhodium, right? So when these lead particles in the fuel end up in the catalytic converter, it poisons certain parts of the catalytic converter. Poisons means it reduces the ability the catalytic converter has to convert carbon monoxide into carbon dioxide, nitric oxide into nitrogen gas, right? Unburned hydrocarbons into carbon dioxide. These are the things that catalytic converters do, right? Makes it better for the environment. But that action will be hindered when it is poisoned. So similarly, this catalyst can be poisoned by adding organic substance known as quinoline. So some students think this is quinoline. No, this is not quinoline. This substance added with an organic substance called quinoline poisons this catalyst, and now that is a very milder catalyst that will not allow this alkyne to completely turn into a alkane. It stops at the alkene level. Is that clear? So when you add these together, you get that. Okay, clear now? Take it down. Okay, write down new heading. Write down a new heading. Addition of water. Addition of water. Okay, right. So under that please write. Under that please write. when an alkyne is added with Hg2 plus and when alkyne is added with Hg2 plus and dilute sulfuric acid, a water molecule can be added. Across the triple bond. Second point. The produced product is known as an enol. The produced product is known as an enol and is unstable. The produced product is known as an enol and is unstable. Third point. This molecule gets rearranged to form a molecule with a keto group. Right. So now let's pay attention, students. So here, if you add Hg2 plus along with dilute sulfuric acid, usually we write it as H plus and H2O. Now dilute sulfuric acid acidifies the medium. We don't usually use any other acid for acidification of the medium because most of those ions are capable of undergoing, the anions are capable of undergoing further reactions. Like chloride ions can get oxidized to chlorine. Nitrate ions also can interfere in certain chemical reactions and turn into nitrogen dioxide, nitric oxides and all that. So therefore sulfate ions found in sulfuric acid seems to be the most stable type of ions when acidifying a medium, because they rarely take part in any other reaction that is taking place. So to acidify the aqueous mediums of this kind of reactions, we usually use sulfuric acid. Is that clear? Right. Here when you add Hg2 plus and dilute sulfuric, I'll write it as dilute sulfuric for the first time, but you can write H plus H2O or Hg2 plus and dilute sulfuric acid. What you form is this. A water molecule gets added across the double bond, right? A water molecule gets added across the double bond. Now water molecule has what? This is a water molecule. So a water molecule will break and hydrogen and OH groups will be adding across the double bond. So one part will get the hydrogen, the other part will get the OH. Right, so there was a triple bond, the one pi bond broke and connected to hydrogen, or the other end connected to OH. Is that clear? Now again, in this case also, although we don't come out in the open and talk about Markovnikov's rule here also we have to make sure we add the hydrogen to the place where there's more hydrogen. In this particular example, both sides had the same amount of hydrogen, so we didn't have a problem. Is that clear? So we produce something like this. Now this is referred to as an enol. ene indicates a double bond. We know ene indicates a double bond. We know that. And OL indicates the presence of a OH group, enol, right? So we normally don't write the dash here. We call it enol. Now these are unstable. These are unstable. They can't stay as an enol for too long. It gets rearranged to form an aldehyde or a ketone. So the keto groups mean aldehyde or a ketone. If the OH is present in a corner part like this, what happens is this section, this OHCH section, turns into aldehyde group, right? So the entire section along with the double bond over here, it turns into an aldehyde group. Is that clear? So it's all of a sudden, since this is very unstable, the atoms get rearranged and forms that. Is that clear? There's nothing needed to be added here. After the enol is formed, since this is unstable, it automatically gets rearranged to form that. Here you will see when I add Hg2 plus and dilute HCl, not HCl, H2SO4, we produce something like this, CH3. Now can someone tell me where the hydrogen would go? Now water molecule is being added here. Where would you add the hydrogen? Left or right? Say left side carbon or right hand side carbon? Right hand side carbon. This has more hydrogen, right? So therefore hydrogen goes here. The OH group goes here. Now the OH is in the middle. Can we form an aldehyde? Because the oxygen's position is now in the second carbon. Here the oxygen was in a final carbon, in a corner carbon. So can we form an aldehyde from this? No. What we usually form here in this case is a ketone, right? CH3, the carbon with the oxygen, there was an oxygen containing carbon here, it becomes a double bonded oxygen. And the other part becomes another alkyl group. So basically this carbon had an oxygen connected to it, that part becomes a double bonded oxygen like so. Is that clear? So now it is a ketone. This is a aldehyde, the top one is aldehyde, the bottom one is a ketone. Is it understood? Can someone tell me the name of this? This is eth and al. Aldehydes end with the suffix al. What is this name? This is propanone. Propanone. Is that clear? Right, take this down. Now students, I told you that it is, what do you call it, dilute sulfuric. Just want you to know that this is often written, now the reason why I am writing as dilute sulfuric is because you need to remember the reagent. This is often written, I erased it earlier, I wrote it and erased it earlier. This is often written like this, Hg, H plus and H2O, right? H plus indicates the sulfuric acid because sulfuric acid brings in the H pluses for the medium for this reaction to be feasible. And water shows here the addition of water because addition of water happens here. So here when you write dil sulfuric also the same thing happens. Dil sulfuric has H plus, dil means it's an aqueous medium. So therefore water is there, right? It's quite a lot of water is there. But more than this form, we commonly use this form. I just wanted you to know both. That's why we write it down initially like this. Going forward, you will just see me writing Hg2 plus, H plus and water. Okay, are we done? Take it down fast. Right. So the last topic under alkynes, you can write the acidic nature of alkynes with terminal hydrogen. Now students, before I complete this diagram, I will quickly teach you something here. The hydrogens that are connected to this carbon-carbon triple bond, whenever you have carbon-carbon triple bond, those carbons can only have one more bond, because triple bond accounts for 3 bonds, it can have one more bond. If the other bond happens to be a hydrogen, those hydrogens are referred to as terminal hydrogens, corner hydrogens. Is that clear? So this is referred to as a alkyne with a terminal hydrogen. Is that understood? So that means the carbon-carbon triple bond is towards a corner of a molecule, resulting in formation of a hydrogen connected to a triple bonded carbon. So this is referred to as a terminal hydrogen. These terminal hydrogens are slightly different compared to normal carbon hydrogen bonds. Right, these hydrogens connected to this carbon is different to the hydrogen that is connected to a carbon triple bond. Okay. Now what is the difference? We say these guys are more acidic than these carbon hydrogen connected hydrogens. Oh, imagine the hydrogen atoms that are connected to this carbon is less acidic compared to this hydrogen. Is that clear? Now what do we mean by acidic? Acidity. What does that mean? Okay, what is an acid? Definition of an acid? Anything that can release H plus ions in aqueous medium. And then later on we say anything that can donate a proton is referred to as an acid. A base is referred to as something that can accept a proton, or base is referred to as something that can donate a lone pair of electrons. Is that clear? So here these guys are acting as an acid because this carbon hydrogen bond can easily be broken and this can be released as a H plus. Right, the acidity of this is actually quite not that high, but still it is referred to as an acidic substance. Is that clear? Now there are more acidic things than this. For example, we say alcohols are also acidic slightly, and we say water is also acidic. Right, water is acidic, aldehydes are acidic. Now water can release H plus. If you take water, it has certain amount of H plus, the medium, right? Alcohols also can release H plus. So for example, alcohols can react with sodium, producing hydrogen gas. So that is an indication alcohols can react with H plus. Alcohols can react with sodium is an example of acidity of alcohols. Now these hydrogens are also acidic. Now we have to explain why it is acidic. Now that's what I'm doing here. Now if you take each of these carbons, if I take, now this is the carbon here, it has sp3 hybridized orbitals. sp3 hybridized orbitals are quite elongated, students, and then it is connected to 1s orbitals of hydrogen, and this is where the bond electrons are. This is where the bond electrons are. Bond electrons of the carbon hydrogen bond of this particular CH3 group is demonstrated that way. You can see sp3 hybridized orbitals are long. So therefore when the s orbital of carbon hydrogen bond is overlapping, it actually makes a bond where the bond electrons are further towards the hydrogen atom than towards the carbon. Is that clear? So you can see carbon atom's nucleus is here, hydrogen is here. Since sp3 hybridized orbitals are a bit longer, the bond electrons are not necessarily further towards the carbon atom. Is it understood? It is somewhat towards the hydrogen atom. Is that clear? Right. But if you take this particular scenario, this carbon has orbitals that are sp hybridized. Those are sp hybridized. Right, those carbon has electrons, orbitals that are sp hybridized. And if you take hydrogen orbital, we'll say 1s orbital of hydrogen, these are carbon orbitals. So now compared to these bonds, right, this particular bond, now if I copy that bond here, we have the carbon atom and the sp hybridized orbital like so, and the hydrogen atom here. This is sp3 hybridized, and this is 1s orbital of hydrogen carbon. Do you see in this particular case the electrons are somewhat closer to hydrogen? Now carbon is the more electronegative element. It should be the one that is attracting all the electrons. But due to the hybridization, the bond electrons are further away from carbon. Right? If you take the electronegativities, carbon is 2.5, hydrogen is 2.1. Can you remember those? Right? Carbon's electronegativity is what? 2.5. Hydrogen is 2.1. Carbon is more electronegative, no? It should be the one that is having the electrons closer to itself due to electronegativity. So it is trying to pull these bond electrons for sure. But the orbital elongation due to the hybridization causes the normal carbon hydrogen bonds, like these normal carbon hydrogen bonds, to have the bond electrons not necessarily quite close to carbon. But in this case, it is close to carbon. Now, don't forget, now imagine now hydrogen is also somewhat close to it, carbon is also somewhat close to it. But when you are comparing the pulling power of the two, hydrogen is having only one proton, carbon has 6. Is that clear? And we know the electronegativity also is high in carbon. So what happens? These electrons are somewhat closer to the carbon nuclei. This causes a bit of a polarization of the bond that makes it easier for these electrons to be given to carbon entirely and for hydrogen to leave as H+. Is it understood? This is why the carbon-hydrogen bond in the terminal hydrogen atoms are easily breaking. Right? So then these hydrogens are referred to as acidic hydrogens because they can break relatively easily. The word is relatively easily compared to a normal sp3 hybridized carbon hydrogen bond. Is that clear? But this is not like super acidic. You can't use this as an acid. It is super weak as an acid still. But compared to the normal carbon hydrogen bonds with sp3 hybridization, these ones are Relatively more acidic. The word is relative. Understood? Take it down. Let's take it down. Let's take it down. I will erase this part because this part is confusing. I think we can take that directly. You can write under this when it comes to alkynes with terminal hydrogen, they are said to be relatively more acidic. When compared with carbon-hydrogen bonds, with sp3 hybridization. Can write as a new point. sp3 hybridized orbitals are more elongated. sp3 hybridized orbitals are more elongated and causes the carbon-hydrogen bond electrons and causes the CH bond electrons to be further away from carbon. New point. When considering terminal hydrogens, the CH bond is formed through sp hybridized orbital. The CH bond is formed through sp hybridized orbital. Causing the bond electrons to be relatively closer to the carbon atom. Causing the bond electrons to be relatively closer to the carbon atom when compared with sp3 hybridized carbon. Therefore, it is considered to be easier. For sp hybridized carbons to. Therefore, it is considered to be easier for sp hybridized carbons to take those bond electrons and remove hydrogen as H plus ions. Right. Oh, you didn't take this one, no? Can you please take this down now? Don't take these arrows down, just want you to Students, I will give you a break after we are done with alkynes. This is the last reaction. We are done with alkynes after that. You can just take this down directly. So let me explain to you what is happening here. Sodium is a reactive element. It can get oxidized, that means it can turn into sodium 1 plus ions by removing an electron. And here normally we know sodium reacts really well with acids. It reacts with water as well. Water also has acidic properties. This also has acidic properties but little less than water. So the reaction would be a tad bit more difficult for sodium than the reaction with water. But however, the reaction takes place. Now if you add sodium and paraffin oils where you mainly have CH3 groups without any terminal hydrogens, the reaction won't take place. Right? If you take any alkane and react with sodium, nothing will happen. They have normal carbon hydrogen bonds. But this carbon hydrogen bond is special. That's why the sodium will react with it. Is that clear? And produce hydrogen gas. Normally when a metal reacts with a substance and producing hydrogen gas, it's a indication that the substance that we reacted it with was slightly acidic. Here we have a strong base. This is called sodium amide. So it reacts with terminal hydrogen to form. So here this will remove as a H plus here, and this has a NH2 minus. NH2 minus and H plus will form together ammonia, and then you form this ion. So these are negatively charged ions called acetylide ions. Acetylide ion along with sodium 1 plus ions form what is known as sodium acetylide. Is that clear? Sodium acetylide. Okay. So are you done taking this down? Then write identification tests. Then we are done. Identification tests. So these tests can be used to identify a molecule with a terminal carbon, also terminal hydrogen. Ammonia in cuprous chloride or silver nitrate in ammonia or cuprous chloride in ammonia, right? So these will form. Now here the Cu1 plus ion can attach here. Since it's a very basic medium, the H can be removed. You are forming something like this, CH3. So we form an acetylide ion, right? So acetylide ion looks like this, students, and a negative charge on the carbon, right? You can count 1, 2, 3, 4, 5 electrons around carbon. Carbon can have only 4. If it has more than 4, it is a negatively charged ion. So we have acetylide ion here, and then along with it a copper 1 plus ion is connected. So therefore what we form is this. Now we don't always have to show plus minus, because whenever we write any ionic compound we don't indicate this is plus, this is minus. No? We just write sodium chloride. The only reason why we write plus minus is for you to understand these are ions. This is called acetylide ion. This is a copper 1 plus ion. So this is formed. Usually we don't talk about colors here much. This is a precipitate, but if you are interested, this is usually a reddish precipitate, red PPT. And then even in our syllabus we don't necessarily talk about the color, so but some of you might like to know, that's why I gave it to you. And this is having a, this is also a precipitate, it's a white precipitate. Water insoluble. If you try to dissolve it in water, they don't dissolve in water. You need to know what an acetylide ion looks like. That's it. Do you want to break after doing some questions from this part or before doing some questions from this part? Before moving on to benzene now. Next one is benzene. I will give you about 3 questions from this part, but I want to see whether you prefer it doing after or before. Before? Everyone is okay with before? Before? Okay, before. We'll do it before. I don't have a problem. I just wanted to see whether you all are okay. We'll start simple. This is simple. I feel like it's too simple also. But take this down. These are the questions that I want you to do. Quickly do this 3. For the time being, the very first one is like, I don't think is difficult at all. Again, the fourth one might be easy. Not sure though. I believe out of the lot, if there is any complexity with anything, it would be with just the third one. I don't think anything else is that complicated. It's pretty straightforward. Did anyone get the third one correct? The first one is, I believe, very simple. PD dash is better because what we do is we take barium sulfate and we coat lead on it, not lead, palladium on it. No need of the mechanism, just the product is enough. Students, I just want the steps, not the mechanism. Okay, conversions indicate just a step, not the mechanism, because we don't learn mechanism for all the reactions. No? This is a conversion. Any? Yes. Can I see the third one? Done? It's a bit difficult. Huh? What about you? Third? Good. Fourth one is wrong. Double check the fourth one. Now only we have enough equations to barely give you conversions. Like, this is like the bare minimum conversions, like only 2 steps. I can't give you more than 2 steps in any of these conversions. Why? Because we don't know that many reactions. Now, after we learn the dehydration of alcohols and forming double bonds from alcohols, forming double bonds from halogenoalkanes, then we can complicate conversions for you. Right? For the time being, I can't complicate it much. So what you see here are simple conversions. Now, even to do the simple conversions, you need to have a good memory of things that we have studied. If we can't remember, then we are in trouble. Right? So let's attempt a few conversions, and then I'll clear the board because I can't do the rest of the conversions while I have these with me. I'll attempt the simplest ones for you first so that I can erase them. The very first one is quite simple. We have an alkyne, I'm converting it to an alkene. What is the reaction? Palladium deposited onto barium sulfate, we write PD dash barium sulfate, PD dash barium sulfate, and quinoline. Quinoline. This is the first reaction, that's it. Along with hydrogen, you need to add hydrogen. If you don't add hydrogen, this will not happen, right? So basically, students, you need to add, for a single one of these bonds to break and form a hydrogen containing species here. So in other words, across this single one of these pi bonds, when it breaks, it connects to 2 hydrogens. So we need to have 1 hydrogen molecule to provide that 2 hydrogen, right? So we need to write plus H2 as well, because without hydrogen, adding these 2 only will not do anything, okay, without hydrogen. Because you break the double bond or triple bonds, 1 pi bond is broken, but you need to have hydrogen to convert it into this, otherwise the reaction will not be balanced. So that's a simple one. I would say second and the third ones are somewhat complicated, so I'll leave it be. But I believe this is quite simple. What is the answer here? Please tell me you got the fourth one right. What is the answer? What do you add? Just HBr. Just HBr, that's it. Why complicate life, students? I see some of you are thinking too much about it. What happens when you add HBr? One of these bonds will break and H will go to one place, Br will go to one place. Usually H will go to the place where there is more hydrogen. Starting off, do we have any hydrogens in any of these carbons? No. So let's say H goes here. It could go here or here, one of the places. But let's say I put it here, right? Because this molecule is symmetric, students. If I put it here or here, it's the same thing, because if I rotate the molecule, it's the same thing. Let's say I put the H here, then the Br goes here. That's one bond broken. Now it has another bond that can be broken in the presence of HBr. Now this has already 1 hydrogen here. Now this carbon is having more hydrogen than the other carbon. So the second HBr is, when it is adding up, the hydrogen in the second HBr will go to the place where there is more hydrogen, right? So it will go here, the bromine will go here, something like this will be produced. Is that clear? Understood? So the answer is just HBr, no complications there, right? So that leaves us with the reaction number reaction number 5, reaction number 2, reaction number 3. Can someone tell me which one was the most difficult for you? So I'll keep that for last, and by the time that you get to it, you will find it is easy because we discuss similar reactions. Which one is the hardest for you? The third one. Third one was the hardest. So the least hardest here was what? Out of the lot. No, I mean like out of the remaining lot. Maybe this one? Yeah? These two are like similar. So we'll do this one. Right? So I will erase this middle bit because that is no longer needed. I will erase that so that I can show the conversion here. So if you take this molecule, if you add again our basic thing, hydrogen and palladium coated onto barium sulfate and quinoline, we get to this CH3, C, double bond H, there will be hydrogen here, and we have CH3 here. And to this we can add what? Dilute H2SO4 and heat. Then what happens is double bond will break and form a OH group. So OH group will go to the place where there is more hydrogen. Hydrogen will go to the place where there is more hydrogen. In this case, both carbons have the same number of hydrogen. So without an issue, you form that. Yeah? Is that clear now? I'm pretty sure you guys were planning to add the Hg2 plus something like that, right? So don't do that. No need. See, you need to see the mechanism a little bit. So don't worry. This is how you all start. Like, you all are going to find it difficult at first, even with simple conversions. But the more you stay with the subject, the more you study, it will be easier for you. Now hopefully the second one is easier for you. Now you know the trick. Hopefully the second one would be easier for you. This one. Can you tell me what the answer is for this one? Second reaction. What is the answer for the second reaction? Now you can tell me. Now it should be coming to you, like, what is it? MnO4. After? It's just direct MnO4 addition or what? Yes, correct. So when it comes to this part, students, what you have to do is you have to first, now we have this molecule CH3, C triple bonded H, so triple bond carbon and then H, and we are converting it into this. Now pay attention. Here you can see that there is two OH groups connected here. Now two OH groups are usually formed in diols, right? You didn't learn anything about triple bond being added with something like dilute sulfuric and forming two OH groups across it. So use only the ones that you learned about. So you can form a diol through what? Now this is a diol, right? As soon as you see it, you have to recall, okay, this is two OH groups are present here. What is this? A diol. So how do you form a diol? Through an alkene. So I need to convert this alkyne into alkene first. So let's do that. We have this. We now know we can add hydrogen, palladium coated on to barium sulfate, poisoned by quinoline. Will form CH3, C, double bonded carbon, and then hydrogens like so. And then if you add just Alkaline medium KMnO4. Alkaline medium KMnO4, the thing that is happening is basically a glycol formation or diol formation. Across this double bond, two OH groups will be attached. Right? Is that clear now? That's the second question. Okay now, right? So the last one, can I erase this one? The third one. So the third one says we have this turning into CH3, CH2, CH2Br. So now students, again the same story. This hydrogen along with palladium, this is an important reaction at this stage, right? Because you don't know many other important reactions. So you are currently limited to these reactions, not very fancy ones, simple ones, right? So then we need to convert it into this. Now you would have gone ahead and added HBr happily. But addition of HBr will not get you to that product. Why not? Hydrogen will go to the place where there is more hydrogen. Bromine will go to the place where there is less hydrogen. Is that clear? So if you do that, bromine comes to the middle carbon. Is bromine in the middle carbon? No. What do you add? Peroxide. Right? So you can add a peroxide. Or you can just, sometimes they will give you a peroxide, right? Sometimes they will give you in a question, this is there. They will give you a peroxide in certain cases. So then use that peroxide. Don't write ROR thing. Is that clear? Then it will be wrong because you have to use the ones that are given. No? So you have to use the peroxide that is given. Sometimes they can give you hydrogen peroxide. That's also fine. Hydrogen peroxide is also peroxide. Is it understood now? Okay everyone, so I went with 2.5 hours without giving you a break, my goodness. Right, so not bad, like you all can go for 3 hours also. It's the same thing. So, okay everyone, so take a small break, take 20 minutes, be here by 5:55, right? And we'll start from there onwards, okay? Now students, I'm sorry, before you take the break, 2 minutes, okay? Are you all free on Thursday? This coming Thursday? And Thursday after that? Yeah? So we will have to have a catch-up class for, like, you know, two consecutive Thursdays because of the POE that we missed, and I'm going to miss the next Monday. So for 2 consecutive Thursdays, we'll have to have a catch-up class. Okay, for the POE day that we missed the class. Was it a POE or Thai-Pongal? POE. So POE day missed class as well as the class that I'm about to miss next week. I'll be out of the country for personal reasons, students. So I'll not be there next week. For 2 Thursdays, we will have to have a catch-up session. Okay, so that will be not this coming Thursday, the Thursday after and after that. Is that clear? If you prefer to have it on the same day, we can arrange that as well. Tell me whether you like to have a catch-up class on the same day if you don't want to travel again on Thursday. You can talk to me after the break and tell me what you prefer. What do you prefer? Who prefers on the same day?
Thursday morning.
Afternoon. Thursday afternoon. Thursday afternoon is not available. Oh, you guys are talking about morning. Okay, I can do a morning. Friday morning. Friday morning is fine with you? How come you all are busy on Friday mornings? It sounds. Monday morning? Guys, Monday morning? Fine? Everyone? Monday morning is okay? For 2 consecutive weeks, huh? It's okay, cut it. How are you going to do the term test? Tell me that. Like, when do you have term test? From next month onwards. How many days? Sorry? Until Thursday. So next Monday I'm not there. So the next week Monday onwards only I'm talking about. You understand? So the coming month, not this Monday, the Monday after that, the whole day, right? I'll have a bigger break in the middle. We'll start around 9. So then we can utilize the whole day. And I'm planning on converting that into a paper class. So that trend will continue. The whole Monday allocation, keep it for me. So then I can convert that into the paper class after these 2 weeks pass. Okay? Or maybe I can do, that's a good thing. I can, like, for the first 2 weeks, without any this thing, I will have one of those morning classes converted into a paper discussion class. So otherwise you will be too bored with all the theory that's going on. Yeah? So we will have the missed classes, we will start with papers. But it will not go as a separate class at that point. It will be just a catch-up class. Later on, after this month, after the February month, I'll continue the entire Feb month like that. After the February month, we'll convert it into a paper class. Okay? Are you okay with the entire Monday being taken? From going forward, you have a class? No? So going forward, the entire day of Monday will be allocated for me. Okay? We will start early. We will finish a little early because we are going to have the same day. We'll break it into few sessions. I'll tell you the plan. Okay? Is that clear now? Take a break. I'm sorry. You can take a break till 6. I took some additional time. So I'll let you know of the plan after that. Right, students, there were some questions that I have given you in the past that I haven't checked. So we will quickly go through those, because without properly figuring out whether you have gotten those correct, moving forward would be somewhat risky. So can I have the questions that I have given you? Let's start from the past. That anything that I haven't discussed. Right, thank you. So write the structural isomers for this formula. C4H8Br2. Now this one has many structures. Starting off with a bit of a difficult one. In a sense, it's a time consuming one. I'll quickly show it to you. So we have C4H8Br2. So basically it's a alkane. Now I'll just draw the carbons and the bromines, and that's enough. Right? Pay attention here. C4H8Br2.
There's one down. I have to do homework.
Okay. This is the one, we have done this one.
Yeah.
Okay. Draw all the structural isomers for C4H8O. C4H8O. Let's do it. C4H8O. So that should be something like 1, 2, 3, 4. So since this is C4H8O, we are looking at aldehyde or a ketone. Let's see if I'm correct here. So we have 2 here, 2 here, 3 here. So there's 4 here, 3 here, 7, 7 plus 1 is 8. So we have this structure. I'm asking for structural isomers. We have the aldehyde form. We can write a ketone as well, like this. Right? Second form. We can draw another aldehyde here. I didn't write it earlier, so let's write it now. Right, so this is another aldehyde that can be formed. Any other aldehyde? Any other aldehyde? No. This is all the aldehyde. These are all the aldehydes that we can form. I'm just looking at it and trying to figure out whether there are any other aldehydes we can form. Not necessarily. No. Okay. So now we can move on to ketones. Can we form another ketone after this? Can we use this to form another ketone? Can I shift this here and get another ketone? No. Then what else can I form here? I can form now. I can see we have come to only a few isomers. No, you have written a few. That's good. Right. So we have the ability to convert this into an alcohol group or an ether group. But if you are trying to convert it into an alcohol group or an ether group, you have a small thing to consider. For example, imagine you convert the O group here into an alcohol group. So you are losing the double bond that was present here. Now, to make sure the number of hydrogens remains the same, you need to make sure the double bond number also remains the same. So if there was one double bond, the number of double bonds here in the next structure should also be the same, so that we make sure the hydrogen number is not going to be different in both cases. So now if you observe here, when I put a double bond somewhere around here, we complete the molecule like this, and the number of hydrogens are okay. 3 here, 3 here, 4, 5. Sorry, 3 here, 3 here, 6, 7, 8. Hydrogen number is okay. So the double bond is here. We can form something like this as well. Now here we have the double bond in the terminal position in the corner carbon. 1, 2, 3, 4 carbons. Hydrogen number is also balanced, no problem here. Apart from that, we can also have another alcohol. Now I'm trying to finish off all the alcohols. You can have a enol. Yes, it is not stable. Yes, enols are not stable, but we are trying to draw the structural isomers. And I have not mentioned in this particular question to take stabilities into account. So therefore, you may draw a enol like this, right? If you have drawn a enol, that is fine. Now I have shifted it from like between these 4 carbons like this, right? So here also we have 5, 6, 7, 8 hydrogens, no problem. Is that clear? So these are all alcohols, but we are not done with alcohols. We can have other alcohols. For example, I can keep shifting this OH group. So we can get other alcohols. For example, I can shift this OH group here and get a different type of alcohol. So from this molecule, I can get this form, CH3, CH double bond carbon here, OH group here, and then CH3 group here. So now that's a different alcohol that I have formed by shifting this OH to this second carbon. I can't shift it again to the third carbon because I'm going to get the same thing. Now here I can shift the OH group to this carbon as well as to this carbon. So I can produce like a few. Now I can continue on writing, students. I think this exercise was given to you to get you all to think. So there is another OH group that is present here. I can write another one, CH2 C. There's a double bond here. There is a OH here, and then CH2 CH3. Okay, I can't shift it here to this position because if I do, I'm getting this. So these are the isomers that I can get stemming from that. And I can't shift this here to any other place also, because if I keep shifting this to different places, I'm either going to get this or that. So those are the main isomers that we can get from alcohols while keeping the main carbon chain as like a 4-membered carbon chain. I can change it to a 3-membered carbon chain by having a branch. Then again, students, it can lead to other products. So this will have many isomers. So at home you would have actually spent quite a bit of time. How many do we have already? 1, 2, 3, 4, 5, 6, 7, 8, 9. Did anyone write 9? No, right? Now the reason why I'm not proceeding that much from here to the I will only draw the ones with 4-membered carbon ring, right? Otherwise, not carbon ring, carbon chain. Because if I bring this here to this carbon, I can draw many other variations, but at least 3 more isomers from that. And then apart from that, we have ethers. For example, things like these. I haven't even touched on ethers. Alright, so here we have 5 carbons and 5 hydrogens, 3 hydrogens there. It is now, having the correct number of hydrogens. This is an ether. And I can have an ether like this as well. You understand? So, those are the main ethers I can think of. And we can introduce a branch, right? CH3 CO I'm running out of carbons if I'm going to introduce a branch, students. Can't introduce a branch. Maybe this way I can. Right? So that's another isomer. So you can get a few isomers like this. Now I don't want to go further than this point. There are few others, but I think by now itself I have drawn more isomers than the ones that some of you would have drawn. So since we came all this way, now ethers, I thought there will be many more. That's it. There aren't many more. Maybe we can explore the three-membered carbon ring here. So when it comes to alcohols, I'll draw them here. We can think of alcohols with just three carbons in it, like this. CH3. We can have the OH here to begin with, or we can have the OH here. Three, CH3, 4. There should be another carbon, right? 1, 2, 3. Yes, there should be another carbon. 1, 2, 3, 4. No, bear with me. Right, so yeah, we can have this or this. Those are the three-membered carbon rings we can have. Yeah, that's it. I think completely. Although I was avoiding writing the three-membered carbon chain, not carbon ring, students. So in the main carbon chain, there's only 3 carbon atoms. So although I was avoiding it, thinking there will be many more, there aren't many more. These are the main 2 ones that we have, because if you shift this OH group over here, it's the same as this one, and I can't shift this OH group to this point without removing a CH3 part. So therefore those are the ones we have. Okay, so yes, yeah, those are the total number of isomers we have. So we have 3 here, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So anyone has drawn 14 altogether? Now there was one example which I didn't give you that had 21. I remember in a class a student requested me to show all 21 and we had to draw all 20. So I'm not going to give you that question. So drawing 21 isomers takes a while, right? So then I believe homework. You have written homework, no? So then it will be easier for me to figure out. I have a feeling against C6H10Br2 geometric isomers. Where was that? Before this. Okay, C6H10Br2. Can I erase this now? Geometrical isomers of C6H10Br2. Okay, how many were you able to draw? 6. Let's see. Bear with me just a second, students. Can someone Right, C6H10Br2, C6H10Br2. So then we have, I'll just draw the carbon connection, students. So then it will be clear to you. 1, 2, 3, 4, 5, 6. We can have the bromines here. Right, so we can have one bromine here and the other bromine also on the same carbon. Right, students, if you have a double bond here, I think I asked you only to draw cis trans, right? Okay. So cis trans means, students, a similar type of groups should be present on both sides. So I'm trying to create similar groups on both sides. There can be many more geometrical isomers called EZ isomers, but you didn't learn about that. So I will quickly draw only the cis trans isomers. Now imagine these two carbons have, like, you know, a double bond between them, and on one side we have CH. If I complete the hydrogens here, CH2Br. On this side also we have CH2Br. So this group is common to both carbons forming the double bond, and carbons forming the double bond all have hydrogens as well. So this is one form. The other form of that would be, the other form, in the sense, this is, let's say this is considered to be the cis form because the hydrogens are facing the same direction. The other one would be this trans form. I'll write it like this. Now I will change this a little bit later. CH2Br. Here I will write the two forms like this: CH2Br, and there's hydrogen here, there's hydrogen here. This is the cis form. The trans form of it is this CH2Br. On this side we have hydrogen, on this side we have CH2Br and hydrogen. So this is the trans form of this molecule. Now I'll keep modifying this molecule, it will be easier then. So then I can shift the bromine from here to this position. So that will produce this type of geometrical isomer. So one side we have CH3, here we have Br and hydrogen. Here I have Br, CH3 and hydrogen. So this is the cis form, and the trans form is this. And apart from these two, now this is transforms. Apart from these two, now those are the main answers. This is what I keep editing. Now I need, like, you know, when it comes to geometrical isomers, you only learn about cis trans. So that means the two different groups connected to this carbon with a double bond should be seen on the other carbon as well. The two different groups connected to this carbon should be seen on the other carbon as well. So now I can change the position of the bromine again, right? I can change the position of the bromine again. I can put it here. I can take bromine from here. Then I can put bromine here. Is that clear? So then I would form this. I will just draw the cis form, students. You can figure out the trans form. Otherwise I'm spending a bit more too much time on this then. CH3, CH2, CH3. The bromines are going to be found here. Br, Br. So you can write the trans form as well, right? So now, are we done? Are we done? Can we have something else? Yes, we can have something else. That is, we can take a CH3 group from here, connect it here, right? CH3, CH3, but we can't forget about the bromines. We can have the bromines here. Okay, so then you get this type of molecule. I'll write it here. I always will write the cis form. You can figure out the trans form. CH2Br, CH2Br, and on the side we have CH3 and CH3. Is that clear now? When it comes to that, also you will have cis and the trans form. Altogether, how many geometrical isomers, cis trans isomers? 8, right? Altogether 8. But those are only cis trans isomer, students. If they ask you, they wouldn't ask you because you didn't learn about it. There's another type of isomer called EZ. But if you are drawing EZ isomers, you can draw many more. But if you are talking about cis trans, these are the only cis trans isomers you can draw using this structure. Is that clear? So cis trans usually say you should have a carbons with a double bond is a must. That's the first requirement. And each carbon should be connected to 2 different groups. And the same different group should be found on the other carbon as well. Right? Those 2 different groups should be found on other carbon as well. So that is a requirement for cis trans. And eventually I spoke about the mechanism, right? The HBr addition. Yeah? What is the molecule? CH3.
CH3CH, double one, CCH.
Yeah. 2 methyl groups, right? I can see it from, yeah. CH3CH. This was the molecule that I have given. I will put the hydrogen and CH3 parts on top. It will be easier for me to work then. Now I have done this theory, so I'll quickly tell you which areas you are going to be getting marks when it comes to the exam, right? So when it comes to your test, I want you to focus on these parts when answering such a question. Pay attention now. HBr, you need to include their partial charges. This is a point to be considered. So I'll just write points. There's 1 point. These are not marks. All these points should be there to gain the total marks. So we'll call this point number 1, right? This. And then there will be this is an electrophile. So this double bond will start giving electrons to this electrophile. So we show the transfer of electrons with a curly arrow with a full arrowhead. So therefore what happens, students? That indicates both the electrons are given to hydrogen to form a bond between these 2. So drawing that curly arrow with the full arrowhead is another point. Hydrogen can't have 2 bonds, so this bond breaks. This curly arrow is another point. So keep in mind, students, when we are drawing a curly arrow, the base of the arrow should be connected to wherever the electrons are. If it is in the air, like this, you are losing that mark. Okay, so don't lose marks just because you forgot to connect it to the bond. And then we have the correct intermediate drawn. Drawing the correct intermediate. Now at the exam, students, when you are doing your paper, you are most of the time not asked to draw both the products. If they specifically ask you, then you have to, but most of the time they don't. So at that point, when you are drawing the major product, you need to be careful and correctly draw the intermediate of the major product. So these are called reactive intermediates, carbocation. So here, where do I put the hydrogen? Where does the hydrogen go? To which carbon? To this carbon or this carbon? Left hand side carbon or the right hand side carbon? Left hand side carbon. Why? There is a hydrogen there on that. This carbon doesn't have any hydrogens. Hydrogen will go to the place where there is more hydrogen. He is looking at these 2, there's another hydrogen, and then it goes there, right? Hydrogens are friends, so they will go and hang out together. which leaves this positive. So this is a tertiary carbocation. So getting the tertiary carbocation intermediate gets you a mark along with the positive charge on carbon. And then don't forget the Br. Now Br is now minus. Now bromine has additional pair of electrons that was not there earlier, because this bond electrons are given to bromine. This represents the bond electrons that were given to bromine. So those bond electrons now turned into lone pair of electrons can be donated to this carbon. So drawing bromine will get you a mark, and drawing the lone pair on bromine donated to the positively charged carbon gets you a mark, and eventually the final product. Final product will also get you a mark. So there are about altogether 1, 2, 3, 4, 5, 6, 7 different things to be addressed here. For usually these 7 different things, you get about 4 marks in total, right? So they are spread across those points. So all of those should be properly shown. Is that clear? What kind of carbocation is formed here? Primary, secondary, or tertiary? Tertiary. A very stable type of a carbocation. Is it understood? Any questions? No? So I have drawn only the major product. If you are asked in the question to draw the minor product, you can draw that, right? So minor product is where the positive charge comes onto this carbon, producing a secondary carbocation. So then you form a different product. So the bromine is going to be attached to this position, right? Okay, that brings us to today, right? Okay. Now we move on to benzene. First aromatic compound that you are going to be learning about here. Now, so this benzene is a interesting compound, because when in the past, when they found out the formula of benzene, one of the problems they had was about the structure of benzene. Now I'm not going to spend a lot of time here, because I will today give you a bit of a history about this and the important details, because this is important. After that I will directly move on to the most important reactions revolving around benzene. Now the benzene's formula is C6. Is this off? It's off, right? I'm sweating. Can I have that remote? Was there a power outage? That's right. Okay. So the initial problem with benzene was when the formula of benzene was discovered. They were not able to figure out what the actual structure of benzene was like. So after many different experimentations and different theories, a scientist named Kekulé suggested a structure, and to date we use it, although it is not 100% correct. Even in our textbook we still use it, right? It's called the Kekulé structure for benzene. So Kekulé structure for benzene is this. We have carbons bonded to one another with alternating double bonds. Normally it is indicated like this. Students, we usually draw benzene in this orientation, but you get it right. If you draw it like this, or this is the same thing. It's like standing up, this is sleeping down. So it's the same thing. So don't get confused. So anyway, this is the skeletal structure of benzene. This is what I'm trying to complete here is the basic structural formula of benzene. Sorry, I keep drawing two hydrogens. No, each carbon has only one hydrogen. Okay. Is that clear? So now Kekulé suggested this structure, and at the time even the scientists around that same time period was also able to accept this structure based on the other reactions evidence that they had. But later on there were some issues with this structure. Now this structure suggests that there are 3 double bonds, alternating double bonds in this 6-membered carbon ring. 6-membered ring. This is a ring, not a carbon chain. This is a ring, right? So even if there is a ring structure like this with alternating double bonds, if you add bromine to this, bromine, what does it do in the presence of a double bond? What does bromine do? What does bromine do in the presence of a double bond, carbon-carbon double bond? Yes, it loses its color and indicates the reaction has taken place, a bromine water test, right? So basically bromine should get added across these double bonds, and therefore the bromine's color will be lost. That did not happen. Okay, so that raised some questions. Why is bromine not reacting? And the other thing is, when it comes to hydrogenating these bonds, they realize it is not that easy to hydrogenate these bonds. Now normally, if there is any other double bond, you add nickel catalyst and then hydrogen. If you add nickel catalyst and hydrogen, bond will quickly open, hydrogen will be attached, saturated hydrocarbon will be formed. Right, so basically this will get converted into, if I added hydrogen, this will get converted into a saturated cyclic compound. That means no double bonds, like this. That didn't happen either. Right, and for hydrogenation they had to spend a little bit of additional energy, or it was difficult to hydrogenate. Right, they needed a specialized catalyst called Raney nickel to do this. But if you do something like this, for example, if you take a normal cyclic alkene, that could easily be hydrogenated, no hassle. But benzene is giving a bit of trouble, right? Benzene was giving a little bit of trouble. So that was another issue we had. And apart from that, we looked into enthalpy as well. I'll talk about that gradually after you get into that part. And the very last thing that kind of made us realize this structure was wrong for benzene is the analysis of the bond lengths. There's something called, students, X-ray crystallography, X-ray diffractions crystallography, or we do analysis with the use of a X-ray diffraction machine, and when you put a sample of benzene into that, or any other compound for that matter, we can find the distance between different atoms here. So it is used to get the bond lengths of different molecules, not just benzene. Bond lengths of any molecule can be calculated using this. But when we put benzene over here, according to Kekulé's structure, we should have carbon-carbon double bonds, which are usually shorter because of the double bond nature, and we should have carbon-carbon single bonds, which are usually longer. So that means definitely, if Kekulé's structure is correct, when I analyze this through the X-ray crystallography or diffraction crystallography, I should get two different bond lengths present in this molecule. So the computer program should say okay, in this particular molecule there are mainly two carbon-carbon types of bonds. One are double bonds, one is double bond, the other one is single bonds. But the machine didn't say that. Machine said there was just one single type of bond, and that bond length fell between carbon-carbon single bond and carbon-carbon double bond. Is that understood? That bond length fell between carbon-carbon single bond and carbon-carbon double bond. Is that understood? So that is what we learn here. So after this, it was evident that first of all I show double bond single bond scenario. So this is like not a double bond, not a single bond, somewhere in between. So that was evident. That was the final proof that we needed to realize that this is wrong. So this structure that we draw, even now we keep drawing it, this is not necessarily the true structure. There's a different structure for benzene, but we can say that structure stems from this. And can you remember this resonance hybrid story that we learned? We can explain it through that as well, and I will explain to you the actual structure of benzene. Okay, so take a new heading, benzene. Take a new heading, benzene. And then write a new subheading, Kekule, K-E-K-U-L-E. Kekule's structure for benzene. Kekule's structure for benzene. You can write Kekule's structure for benzene was a structure suggested in the early stages, that is now proven to be incorrect. So then write this C6H6. Right. So then after that, please write evidence that the Kekulé structure does not correctly depict or correctly show the real structure of benzene. Evidence piece number 1. Number of isomers of disubstituted benzene. Now students, first of all, now something that I want to say before we move any further, I should have mentioned in the beginning as well, is compounds that contain benzene. Now benzene structure is slightly different. It's not just a normal cyclic compound. Compounds that contain benzene are referred to as aromatic compounds. Now back in the day, chemistry was simple. If something smelled nice, if the compounds that we analyze are smelling nice, they say nice smelling compounds, no? And then they name it based on that. What is it? Aromatic compounds. Or if it has a distinct smell, we say aromatic. So benzene and compounds that have a benzene group and is revolving around derivatives of benzene are usually referred to as aromatic compounds because they have somewhat of a distinct smell, right? Or they have some sort of smell. So some compounds, for example, if you take sodium carbonate, you don't have a smell, right? So you don't necessarily feel a smell. But things like ammonia, sulfur dioxide, nitrogen dioxide, those will have smells. But as a group of compounds, benzene containing groups usually have somewhat of a smell. That is why we call them aromatic compounds. So back in the day, that's how they named it. But now we have so much, we have discovered so many different other compounds that has benzene rings in it. Some of them wouldn't have a smell in it, but still we call them aromatic. Is that clear? Right. So now, when it comes to benzene molecule, students, going forward, we will use this Cadle structure. I can't be showing you the, structural formula, displayed formula like that all the time. That is a displayed formula. This is Cadle structure. But just for the time being, I will show something here. Now, in the first piece of evidence, we talk about disubstituted benzenes. Disubstituted means, students, if you remove one of these hydrogens and in place of it, if you have something else, then it is referred to as a substituted group. So when you have one substituted group, it is referred to as a mono-substituted group. If there are two groups, imagine another hydrogen was substituted by something, then it is referred to as a di-substituted group. Is that clear? Right. Now, when it comes to benzene, once a single group is attached to it, we will usually start numbering the carbons from that group onwards. We don't take this carbon into account. I'll attach different groups so that you don't get confused. I will attach something like a chlorine here. So now this carbon has its hydrogen substituted by a different group. So we'll start numbering the benzene ring starting from that carbon. First carbon, usually we prefer to go in the clockwise direction. First, second, third, fourth, fifth and sixth carbons. Okay. Now compared to starting from this place, the second and the sixth positions of these monosubstituted carbons are usually referred to as the ortho positions. We call these positions the ortho positions. And the third and the fifth positions are referred to as meta positions. Meta. And the fourth position, that is directly in front, directly opposite the substituted group, is referred to as para position. Is that clear? Right. So now students, when I have, let's say, a disubstituted benzene, we have a chlorine. I'll try to draw the same molecule that I have drawn here. So I have drawn the benzene molecule like so. Now imagine I am attaching a bromine. I can attach a bromine here to ortho position, right? And then I can also attach a bromine, let's say, to a meta position, or I can directly attach it, here. Directly opposite to the first group, like this. So this is referred to as a now we can write the name chloro-bromo disubstituted group, again another disubstituted group, so we can write the positions as well, 1, 2 here, 1, 4, so 1, 2, 3, 1, 3, and then 1, 4. Okay. Now according to the Kekulé structure, now in benzene, in real benzene, if you have a disubstituted benzene molecule in real benzene, you only see 3 isomers like this. It's either right next to chlorine like so, somewhat away from chlorine in the meta position like this, or para disubstituted one. So this is referred to as an ortho disubstituted molecule, meta disubstituted molecule, and a para disubstituted molecule. That means compared to the initial group, the second group was attached to a ortho position. It is referred to as an ortho disubstituted molecule. Compared to the very first group, the second group was attached to a meta position. So this is called a meta disubstituted molecule. Compared to the first, the second group was attached to para position. We call it a para disubstituted molecule. So in the real benzene molecule, you have only these 3 isomers. But if you analyze the we'll take this ortho disubstituted molecule. If you take ortho disubstituted molecule, because that's what they analyzed back then, according to the Kekulé structure, we can very clearly have two different types of isomers, right? You can have a bromine group attached to this ortho position or this ortho position. But the thing is, according to Kekulé structure, those 2 ortho positions are not necessarily the same. Why is it not the same? Because if you take a look at this particular bond, it's a single bond. Chlorine, carbon, single bond, carbon, bromine. Here, chlorine, carbon, a double bond, carbon, bromine. Is that clear? So here, the 2 groups are attached across a double bond. Here, the 2 groups are attached across a single bond. So according to Kekulé structure, we should get very distinct 2 different isomers when it comes to ortho disubstituted molecules alone. But in the real molecule, it doesn't happen. Is that clear? Now I'll give you a glimpse of the real molecule. The real molecule's actual structure is usually indicated through this symbol. You might have seen this symbol. Okay. So attaching a chlorine here and a bromine here would mean the same as attaching the bromine on this side, because there's no distinction, there's no double bonds indicated in this molecule. Is that clear? So this is the first piece of evidence. that we learn about. Okay, write down. First of all, copy this as additional detail, or like no, under that topic important, and write this down. This is something like you will be very used to, but for the time being, right, when it comes to monosubstituted molecules, we start from this point, and every other point I'll give you a small note on it. Write down monosubstituted benzene. Monosubstituted benzene. Again, right? In monosubstituted benzene, the second and the sixth carbon positions, are known as ortho positions. And the third and the fifth positions are known as meta positions. And finally, the fourth position is known as the para position. And take this down, please. Done? We'll hurry it up. So then write disubstituted benzene. Disubstituted benzene. Right. This evidence part is important, that's why I am giving you a note on it. So you can write, when analyzing actual disubstituted benzene molecules, only three distinct, when analyzing actual disubstituted benzene molecules, only three distinct isomers are seen. However, Kekule's structure should produce more than 3 disubstituted benzene isomers. Since more than 3 isomers are not actually found, Kekule's structure is not entirely correct. Take this down. No need to take this down, I'm trying to explain something to you here. Because I want to leave that thought with you before we finish the class. Are we done taking that down? Right. So today, before I finish this part, I will teach you now. This is one evidence, right? So there are no two isomers like this. So that means the Kekule's structure is wrong. But he was like, really good to figure this out. Right? Having something like this, when nobody could properly propose a mechanism, to propose a mechanism like this, he had some sort of knowledge. But later on, experimentally, we realized our structure might not be entirely correct. Right? It could be slightly wrong than what we expect. So I'll give you the real idea here before we leave today. That is, now if you take a look at, according to the Kekulé structure, according to the benzene's formula, it suggests each carbon is connected to only one hydrogen. No? So that means, like, let's say Kekulé structure, each carbon has 1, 2, 3 main groups connected to it. So those kind of carbons usually have what kind of hybridization? sp or sp2, sp3. sp2, no? So sp2 hybridized orbitals usually have 3 orbitals that are hybridized, sp2 hybridized, and 1 unhybridized, p orbital. So these are the p orbitals that I have drawn that are unhybridized. All the other sp2 hybridized orbitals, they are in bonds. Now these p orbitals are the ones that we think are forming the pi bond. The unhybridized p orbitals are the ones that are considered to be making the pi bond. Now, since sp3 carbon, if you take any sp3 carbon, students, it's trigonal planar. sp3 carbon, sp3 hybridized orbitals are like this. They are in a single plane, trigonal planar. And then the unhybridized p orbitals are above and below like this. Now, sp2 hybridized carbons are trigonal planar, and then unhybridized p orbital is like this. sp2, these are sp2 hybridized, and then unhybridized p orbital is present perpendicular to that plane. Okay, so if this is the plane where the sp2 hybridized carbon atoms are there, like, there will be p orbitals coming above the plane and below the plane, because p orbitals have 2 lobes, no? So now, when those kind of carbons bond to one another to form a cyclic ring like this, since each carbon has a flat spread of bonds, what happens? The entire carbon atoms that are forming the 6-membered ring is on a flat level, right? Not one carbon above, one carbon below, no, not like that. All the 6 carbon atoms are in the same plane, and each carbon atom has a p orbital lobe going up and p orbital lobe going down. This is a single p orbital, but it's above that plane and below that plane, as I indicated earlier with the book. And each of these p orbitals are parallel to one another. This drawing should explain it. And each of them have 1 unpaired electron. So each of these orbitals have 1 unpaired electron, and they are in close proximity. What happens is, instead of forming double bonds alternatingly, now we say these two join together to form a double bond here, right? We write these two join together to form a double bond here, right? But instead of doing that, what they actually do is, since each of these has 1 unpaired electron, they pool in those electrons and form one delocalized electron cloud. Is that clear? They merge all these p orbitals that are parallel like this. They merge all the p orbitals together to form one electron cloud above and below that carbon plane. Is that clear? This is where the carbons are. I told you p orbitals have 1 lobe here, the other lobe is below, right, like this, right? This is a single p orbital. So all the p orbitals, they mix together and eventually end up forming a delocalized electron cloud that is present above the plane and below the plane. Is that clear? And that makes this molecule so stable, right? Extremely stable compared to any other molecule that has the same number of carbon atoms and the hydrogen atoms. This becomes so stable, right? Quite a bit more stable. You'll see, I can give it to you in kilojoules values next week, the stability. So this becomes so stable because of the delocalization of this electron cloud. So we normally draw it like this. Now, these lobes, they join together, top lobes, they join together to form the top delocalized part, and the bottom lobes will also join together. They actually, I can't break it down to top and bottom lobes, but what happens is, in a p orbital there are 2 lobes, no? All the p orbitals join together and delocalize their unpaired electrons and form what is known as an unpaired pi electron cloud. Clear? Which stabilizes this molecule quite a lot. And that is why benzene has a bit of a greater stability compared to other molecules with the same formula. Not same formula, similar formula. Is that clear? Right. So is it understood now? But I have to give you three more pieces of evidence which I'll give you next week. But think about this at home, read about it in the textbook. And then after the structural part is there, students, the equations I will do very fast because there's not a lot of details to be told. Because once you know one mechanism of benzene, if you learn one mechanism of benzene, you will see it's repeating over and over and over again. So if I ask you to draw 3, 4 mechanisms, you will ask me why, because it's the same thing. You will feel like it's futile, like stupid to keep drawing it. So therefore we'll draw about 2 until you get the hang of mechanisms. Then after that I'm not going to ask you to draw the rest of the mechanisms. It's not needed. Even the textbook doesn't ask you. Okay. So with that, I'll wrap it up here. Any questions from benzenes? Anything? Right, we'll stop here, students. Please note that we will not have classes next week. We will be having classes the week after for consecutive 2 weeks on Monday morning, right? So we'll continue that way. So that will be all for today then. I will see you all again in 2 weeks. Right. See you guys.